focused ultrasound is a kind of non-invasive surgical operation. And the tissue ablation is achieved by deliver the acoustic energy to a focus zone and translate them into a thermal energy. This is a very precise operation. Any movements of the patient's body will displace the focus zone and cause a healthy tissue damage. So to avoid that kind of damage, we are going to use the MRI to guide the HIFU. The advantages of the MRI to get the HIFU is, the first one is the tissue temperature can be monitored so that the focus zone can be located. And any movements of the patient's body can be compensated in real time. But it will have some problems. The first, because we need to use a multi-element ultrasound transducer array to use in HIFU operations. But the array may have over 1,000 elements. So if we want to drive those elements by different phase information, the connection setup will be very complicated. So our objective is to design a seamless transducer driver which can be installed nearby the transducer. That will decrease the complexity of the setup as connection setup. There are some challenges. The first one is the driver should occupy minimum possible area because we don't have a large portion of area nearby the transducer. And the second one is the magnetic components such as inductors, transformers cannot be used in this design because they will interfere the MRI operation. And the third one is the driver's efficiency must be as high as possible to avoid overheating. The fourth one is the drivers should be able to deliver over 1 watt of power to the load. And the last one is we must develop a strategy to drive a transducer array. The second chapter, background information and the literature review. The figure A is the expanded view of a transducer. The rightmost component is called resonator, which generated the ultrasound. And the left component is called housing, which protected the resonator and the circuit. The figure B shows the transducer array, which designed by the Jonathan Lawrence Calvin, who was a graduate student in our university. And we derived the transducer array driving strategy by using this transducer array. Before we drive the transducer, we must know the characteristic of the transducer. This circuit is the equivalent circuit of a transducer. This is a combination of parallel capacitance and series resonant branch. So if we plot the transducer on a certain frequency range, we can get a series resonant frequency and a parallel resonant frequency. The series resonant frequency can be found when the real part of its admittance is at maximum. And the parallel frequency can be found when the real part of impedance at its maximum. So based on the parallel frequency and the series resonant frequency, we can get the expressions of all the equivalent value of the equivalent circuit of a transducer, which is the equation 1, 2, 4. So based on above equations, we can get all the equivalent component value of all the transducer elements in that transducer array, which are listed on this table. So there were a lot of the previous design that were proposed by other research groups, and I will list some of them. This design is proposed by Ken and Hao. They designed a Class D amplifier to drive a transducer. The M1 and M2 is forms a Class D amplifier, and with the 2-gate driver to drive these two transistors. The advantage of this schematic is the simplicity and the low cost, but it has some drawbacks. The first one is we need a matching network that has an inductor, which cannot be used in RLI. And the resistors, the resistor M1, R1 and R2 will need a large portion of area, so we cannot use this design. The second one is proposed by Yang and Xu. They use a full-bridge Class D amplifier. Sorry. And this circuit can be driven by the square wave or PWM wave. But it has some drawbacks. The first one is they need a matching network which has two inductors, which is the L1 and L2, cannot be used in the MRI. And the op-amp in this circuit and these two resistors will occupy a large portion of area. Another one is the Tang and Clemens design. They use a harmonic cancellation technique, but they need two transformers. And Zhao et al. Proposed a Class D high voltage pulsar, but the switching loss is high and the phase shift and the duration cannot be programmable. Bozok et al. Proposed a driver for a capacitor ablation system, but the driver's output power is less than 1 watt, so it's not suitable for our objective. We have a previous design that proposed by our group. This is the certain schematic, and we use two transistors to form a Class D half-bridge amplifier with two gate drivers and a combinational logic block. The advantage of this driver is that the switching loss is very low, and but the drawbacks are the driving posturing and the phase shift cannot be digitally programmable, and we need more output power. So my project is to modify this circuit to let them their output power to output more power and to make the phase shift and the ratio can be programmable. Chapter 3, operation of the Class D amplifier. This circuit is the topology of the half-bridge Class D amplifier. The VDS2 is the output voltage, and the I is the load current. The figure B shows the input and output waveforms of the Class D amplifier. We can divide it into 4 intervals. At the first interval, the M1 will be turned on and M2 will be turned off, so the output voltage is VCC. And at the third interval, the M1 will be turned off, M2 will be turned on, so the output voltage will be 0. And in the second and the fourth interval, both the transistors are turned off, so the parallel capacitance will charge or discharge the series resonant branch. So like the zero voltage switching and the zero derivative switching happened. The zero voltage switching and the zero derivative switching will eliminate the switching loss of these two transistors. So that will increase the efficiency of this driver. Before we drive a transducer, we must know the optimum duty ratio and the frequency of the amplifier. So because most of the transducers quality factor is higher than 2.5, so the load currents higher harmonics will be eliminated. So we can get the expressions of the fundamental components of the output voltage and the current from the references. So the equation 5 is the fundamental component of the output voltage. The equation 6 is the fundamental component of the current of the load current. And then we can use the expression 5 to divide expression 6, and then get the effective load impedance, which is the equation 7. And because from the equivalent circuit, we know that impedance of the series resonant branch is the Rs plus j omega Ls plus 1 over j omega Cs. So if we solve the equation 7's real part and the imaginary part separately, we can, for the frequency, we can get the equation 8 and equation 9. In the equation 8, the Fr is the operation frequency we get from the real part of the impedance. And the Fx is the operation frequency we get from the imaginary part of the impedance. So the class D switching occurs when the Fr equal to Fx. For instance, if we plot the transducer A's Fx and Fr, we can get this figure. The black line is the Fr and the red line is the Fx. As we can see, we have two intersection points, which is the class D's operation point. These 2 points value are listed on this table. Because the transducer A series resonant frequency is 998 kilohertz, so we are going to use the second point as the optimum frequency and the corresponding duty ratio for the transducer A. And based on above strategy, we get all the optimum frequency and the corresponding duty ratio of all the 6 transducers, which are listed on the first table. If we drive all of them on by their own optimum frequency and duty ratio, we can get the efficiency result which are listed on the second table. As we can see, the efficiency of all the transducers are nearly 92%, and the output power is over 1 watt, which achieved on the goal. This figure shows the output waveforms of all the 6 transducers driving by their own optimum frequency and duty ratio. And here are some current spikes that caused by some error on the control procedure. It's not caused by the driver itself. It will be eliminated on the experimental test. During this procedure, we also found that there are some transducers that cannot be driven by the Class D amplifier. The transducer TX3 equivalent components are listed on this table. And if we plot the Fr and Fx of this transducer, we can get this figure. As we can see, the Fr and Fx has no intersection point, which means the TX3 cannot be driven by the Class D amplifier. But we still can get an acceptable driving strategy by using the duty ratio sweeping. In this figure, the right line is the efficiency versus the duty ratio, and the blue line is output power. The purple line is the current spikes on the load current. So we found that the efficiency which is maximum at the duty ratio equal to 0.25. So for the maximizing the efficiency concern, we are going to use the 0.25 as the operating duty ratio for this transducer. This is the simulation result of the TX3 by driving by Class D amplifier. As we can see, because of the parallel capacitance cannot charge or discharge this the series resonant branch to its maximum, so it causes a lot of current spikes on the load current. And its efficiency is just 43.3%, and output power is just 227 milliwatts. The chapter for the strategy for driving a transducer array in Class D mode. So if we want to drive a transducer array, we must drive all the transducer elements by the same frequency, because we need to superpose all the acoustical wave on a focus zone. And but every element's optimum frequency is different to each other. Sorry. So if we drive a transducer such as a transducer B on a non-optimum frequency.